All right, let's talk about negative numbers. So there's a really big positive integer. How would I write the negative version of that integer? Just put that symbol in front. If I want to be explicit and write the positive version, I put this symbol in front. Right? That's a human trick. And it's really simple. We just put a special symbol in the very beginning, which means this number is negative. And by default, if we don't have a symbol in the beginning, the number's positive. But if we put this plus sign, that definitely means the number's positive. Okay? That's a version of representing negatives that we call signed magnitude. We have the magnitude of our number, and then we have the sign of the number. Okay? That works well for us. It does not work so well for computers. Because what this means is that if we do something like 14 plus negative 7, we have to know that this is a subtraction problem. And we have to say, okay, this is 14 minus 7, and so 4 minus 7 is 7, and we have to borrow the 1. And we start doing all this crazy stuff, right? Computers, we use a different approach to storing negative numbers. And if we use this approach, we don't have to do anything funny when we have negatives. We can do the same addition algorithm that we use for positive numbers, and it'll work for negative numbers. And this is something called 2's complement. And if you've done Engineering 250 already, you've seen 2's complement. If not, you will. And I don't know how much this gets covered in this course, but let me give you the essential behavior. So we said that, let's just think about 4 bits. So we have 0, 0, 0, 0, all the way up to all ones. I don't need to write these, I just can't stop. All right, so there's all 16 possible 4-bit numbers. And if this is unsigned, then this is 0, 1, 2, 3, 4, 5, 6, 7, and so on. Up to 15, that's 2 to the 4th minus 1, 2 to the 4th is 16. Okay, signed numbers using 2's complement. These are all going to be the same. But this number down here is actually going to be negative 8, negative 7, negative 6, negative 5, down to negative 1. And it's not arbitrary. There's a reason why we do this. The reason we do this is basically because if we were to take the number 5 and the number negative 5 and add them together, we're going to get 0. Right? So we define these negatives to be the thing that when we add to the positive, we get 0. That's how we get the representation of a negative number. And this is almost how always we're going to see negative numbers represented inside a computer. And so for 8 bits, unsigned, we go from 0 to 255. Signed, we go from 2 to the 7th minus 1, which is 127, down to negative 2 to the 7th, which is negative 128. And it feels like we get an extra negative number. We've got 8 negatives, we've only got 7 positives, and then we've got 0. Right? But if we think of these as non-negative, we've got 8. If we think of these as negatives, we've got 8. Right, so it splits in the middle, but 0 looks like it's positive because there's no minus sign in the front. So 8 bits, we go from negative 128 to positive 127. 16, we go from negative 32768 to positive 32767. So it's just different ranges. And so the formula, if you want to do the math, it goes from negative 2 to the quantity n minus 1 up to 2 to the quantity n minus 1 minus 1. That's the formula you just found. All right, so if we use a character for an integer, that's a byte. Unsigned goes from 0 to 255. Signed goes negative 128 to 127. And if we actually put a character in it, it can hold any of 128 different characters. So how do we store a character? It's another arbitrary decision. If we want to store the letter W, we use this pattern of 8 bits. If we want to store lowercase x, we use that pattern of 8 bits. All these patterns, its most significant bit is a 0. And technically, making this first bit a 1 is undefined. It actually does stuff, but generally we think of character values as being a 0 followed by 7 bits. Well, 7 bits lets us specify 2 to the 7th different things, 128 different characters. And that's it. And there's no reason that this pattern of 1s and 0s represents the letter W. Right? It's just arbitrary. But if I use that for the letter W and you use that for the letter Z, and I have a document on my computer and I give it to you to put on your computer, it's going to look very different. All right? And this was a problem when computers were first being developed, because different computers use different ways of coding characters. So a standard was developed, and that standard is called ASCII, American Standard Code for Information Interchange. So 1963, and 10 plus years ago, the web got modern and switched to something called Unicode. And Unicode can be 16, 24, 32 bits. And it lets you represent other alphabets, which is really useful. Because even though a lot of the world speaks English, which is based on a certain character set, right, a lot of the world does other languages as well. So Unicode 32-bit is enough to represent every language that we know of. Every written language, at least, so far. But we still kind of default to ASCII in a lot of our computer stuff, right? And there's an overlap between ASCII and Unicode. So 128 codes, 95 are printable, they're actual letters, $, letters, digits, things like that. 33 are what we call control codes. They mean other things. There's the table. Okay. So our printable characters start at value 32. That's a space in this middle column. Exclamation mark, quote, number sign, and so on. The digits start at 48. Okay, 5 is 53. That's where the 53 was coming from. And then the uppercase letters start at 65. Lowercase start 32 beyond that at 97. And the last character, 127, is actually another control character, along with these in the beginning. And it used to be that these were significant. So there were these old teletypewriters that they were yellow, and they had these big round cylindrical keys, and you'd push it and it would slam this thing up to make the letter, and the whole thing would shake. And they had physical bells on the side of them. And if you had a file that contained ASCII code 7 over there on the left, it would ring the bell when it tried to print that, right? And you could send somebody a message, and you could put character 7s in it, and their terminal would start ringing the bell and going crazy. Character 10 is a line feed. That's what makes the output go down to a new line. 13 is a carriage return. What does carriage return mean? What is a carriage? Where is it returning to? Yeah. So how many people here have actually played on a typewriter? So this is all terminology that that's becoming out of date really quickly. This is a Walmart typewriter for $200. That tells you something. So there's a typewriter. And the carriage is this thing up here, right? So you put a piece of paper back here, you turn this knob, and the paper feeds through the bottom. And each time you type a letter, this whole cylinder that's holding your paper moves one spot to the left. Because the keys are always typing right here, and there's a ribbon here that's covered with ink. Key comes up, hits the ribbon, piece of paper behind it gets an imprint of the key. But your key's always hitting right here, so to move across the page, you actually move the page down from right to left. So that's called the carriage. So carriage return was a button that would cause this carriage to come all the way back here so that you're printing on the leftmost position. Now when we print a carriage return on a computer, what happens, the cursor flies back to the left side, right? But it's mimicking what happens on a typewriter. A line feed was something you could press that would simply turn this knob one spot without moving back to the beginning, so that now you're moving one line down, but you're still where you happen to be in the line. Backspace would move the carriage back one space, and so on. So a lot of these are nods to the older technology, which was basically using typewriters or something typewriter-like for input and output. All right, so floating point numbers. So things with decimal points in them. This is a different business. So we use floating points to represent real numbers. So mathematically, integers are whole numbers. If you want a space that's bigger than just the whole numbers, you usually include real numbers. So things with, you know, something point something, or fractions, or things like that. A 4-byte 32-bit integer only goes up to 2 billion and down to minus 2 billion. If it's unsigned, it goes up to 4 billion. The mass of the sun is, you know, twice 10 to the 30th kilograms. It's a huge number. It's way bigger than a few billion, right? The charge on a proton is 10 to the minus 19th coulombs. That's a tiny number. The smallest number we can represent with an integer is 0. The next smallest number is 1. There's nothing in between. Well, there's a lot of the universe between 0 and 1, right? Anytime you're working with a microscope, you're dealing with these really tiny numbers. If you're working with a telescope, you're working with these really large numbers, right? Not very well suited for integers. So we want a way to represent much bigger numbers. Well, one way to do big numbers would be to just have more bits, right? But 10 to the 30th, we're going to need a huge number of bits, and that's not even a really big number. If we want to look at the distance between galaxies in meters, we're going to need a much bigger number. And we'd end up with these ridiculous big integers, a long integer. So we need a different approach. Well, what do we do as humans again? We're doing it right here, right? We didn't write 2 followed by 30 zeros, because that takes a lot of paper. We wrote 2 and then times, and then we said 10 to the 30th. We didn't write a 0 followed by a period followed by 19 zeros followed by 1 6. We use a different way of representing this number. And the physical space on this page, 1.6 x 10 minus 19, it's not taking a lot of space, but we're representing a really small number. And with about the same amount of physical space on the page, we can represent this really, really big number. Well, the space on this page roughly corresponds to how many bits we might need. Okay, it's a similar conundrum. We only have a certain amount of bits that we're going to use to store these numbers, but we want to represent things that are really big or really small. So we need another convention. And again, different places used to use different versions of coding real numbers, and this got standardized as IEEE 754. And it's a standard way of using 32 or 64 bits to represent a real number. All right, so 4.3 times 10 to the third. Or sometimes we see it as 4.3 exponent 3. That's how your calculator might display it. Actually, I'm just going to turn the lights off because it's kind of nice outside. Okay. 4.3 E3, that means 4.3 times 10 to the third. right? Could we write that 43 exponent 2? Technically, we know what that means, but if we do that on a chemistry test, we probably lose a few points, right? Same thing if we were to write 0.43 exponent 4. And technically, you know, we could do this. And yeah, that's the same value, but that's not really standardized, right? The standard way to do this is like this. Well, why do we know that this is the correct one and these aren't? What's the rule we're using? A single digit after this decimal point. All right, this has got 2 digits, this has got no digits, this has got 4 digits. Right, so the rule is we're going to write some number with a single thing followed by a decimal point, and then exponent whatever we need. Well, we can do this in binary too. Again, we're going to adopt what we already do with decimal numbers, but we're going to do it in binary. And we're going to take our really big binary number, and we're going to say, okay, let's write this as, you know, 1 point something times 10 to something, so that this ends up being equivalent to our original number. So something to note about when we use scientific notation, mass of the sun, 2 times 10 to the 30th, that's a number with 30 digits in it, right? 30 or 31. It's a lot of digits, but most of them are zeros. Does the sun weigh exactly 2 times 10 to the 30th? No. It weighs 2.114723618 blah 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 point blah 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 blah, right? But we round it off. Charge of a proton, it's not exactly a bunch of zeros followed by 1 followed by 6, but we round it off. So we're going to have to do the same thing with floating point numbers. We can't actually represent this big long arbitrary pattern of ones and zeros, but we could round it off. Right? What we could represent is something like 100110001, and then maybe treat all of these as zeros. And then if we try to write this in our scientific notation, right, we may just pick the first 8 or 10 digits and then make that times 2 raised to something that should have been 2 to something. Multiply that by a power of 2. All right, so let's look at some details of this, because that's a hand-wavy high-level view. What does this mean, 101.11? If we just introduce this point in the middle of our binary number, we know what 101 means. Right, so we're just going to work in binary, even though I'm not going to write down the little 2. So what is 101 equal to in binary? If that's a binary number, what's that equal to in decimal? That's equal to 5. Right, how do we know? Because this is 2 to the 0, 2 to the 1, 2 to the 2. This is the 1s, this is the 2s, this is the 4s. So it's 1 times 1, plus 0 times 2, plus 1 times 4. That's 1 plus 0 plus 4. That's 5. So what could it possibly mean if we put some digits to the right of the decimal point? Yeah, it's just negative powers. Right? Again, same thing we do with decimal. If you say point something, that first thing is the 10 to the minus first place, the 10th place. The next one is the hundredths, the next is the thousandths. So this is 2 to the 2, 2 to the 1, 2 to the 0. This is 2 to the minus 1. This is 2 to the minus 2. So this is 4, 2, 1. This is 0.5. This is 0.25. So this is 4 times 1, 0 times 2, or 2 times 0, 1 times 1, 0.5 times 1, 0.25 times 1. So that's 4 plus 1 plus 0.5 plus 0.25. That's 5.75. So we can already represent decimal numbers using this binary coding by just introducing this point. Now, it's not technically called a decimal point because we're not in decimal. We could call it a binary point, but we usually just call it a radix point. Radix just means base. So if we're in base 10, if we're in decimal, it's a decimal point. If we're in binary, it's a binary point. But this point, right, things on the left are powers of 2, things on the right are the negative powers of 2. Still weighted positional notation. So we know how to convert binary into decimal. Do we know how to convert decimal into binary? Like if I give you the number 137 in decimal, do we know how to convert that into binary? This is another thing that we touch on in 120, but we do it more in 250. I'll show you a trick. You can do powers of 2 and sort of play hit and miss and try to find numbers, powers of 2 that add up to this, but there's an algorithm we can use. Okay, take your number, divided by 2. So what's 137 divided by 2? I'm going to think it's 68. Is that right? So it's 68 with a remainder of 1. Okay, so it's 68.5. Well, we'll write it 68 with 1 left over. Okay, take your 68, divide it by 2, and that's 34 with nothing left over. Take your 34, divide it by 2, that's 17 with nothing left over, and just keep going. So 17 is 8 with 1 left over. Four divided by 2 is 2. Say again? Yeah. Careful with this last one. 1 divided by 2 is actually 0 with a remainder of 1. Okay, once you get down to a 0, you can stop. There's 137 in binary. And that always works. And it works for any base. If you divide by 8, you can do this for octal. Well, we can do this in the other direction as well. If we have something smaller than 1, right, something just to the other side of the decimal point, we can do something similar to convert that into binary. So for example, 0.75 multiply by 2 gives us 1.5. Take that fractional part, 0.5, multiply by 2 equals 1.0. And once you get down to 0, you're done. And now we take these bits, 0.11, that's what 0.75 looks like in binary. So there's a question here, convert 10.6 decimal to binary. Well, 10, we can convert 10 to binary by doing this business, or we might just know that 10 is 1010, or we know what 8 is and we could figure it out from there. So 10 equals 1010 in binary. But what about 0.6? We'll multiply by 2, we get 1.2. 0.2 times 2 gives us 0.4. 0.4 times 2 gives us 0.8. 0.8 times 2 gives us 1.6. 0.6 times 2 gives us 1.2. We've got a pattern going now, right? So 0.6 equals, it's going to turn out to be 1001, 1001, 1001, and so on. Right? And if you actually add up these powers of 2, this is 2 to the minus 1, 2 to the minus 4, 2 to the minus 5. Keep adding these up, you get closer and closer to 0.6. But it's not exact. And that can be a weird thing with floating point numbers. If you do 0.1, the same thing happens. It's a repeating number. If we went on forever, if we did some calculus and some limits, eventually this would come out exactly to 0.6. But we've only got a certain number of bits to work with. So if we add these up, it's not going to be exactly 0.6. Does that matter? Depends. If this is a banking program and we're trying to add 60 cents to somebody's account, we're probably not adding 60 cents. We're adding 59 point something cents. There's a little bit of error there. So this is the Office Space ATM thing, right? Yeah. These little errors can add up really quickly. So floating point is really bad for like financial applications. And a lot of times it's not used. We use a totally different way of representing fractional numbers. Now in decimal, you know, the number 1/3, we can't write that exactly. It's this ending pattern of 0.33333. We deal with that, right? But it's there. Well, there's other numbers that we can write nicely in decimal, but not perfectly in binary. So if we put these together, this is the number 10, this is the number 0.6, so 10.6 could be written as 1010.1001, 1001, and so on. All right, so how do we put this together to actually represent a general real number in floating point? So this is the IEEE 754 standard. Basically, we write our number as a fraction times a power of 2, right? So let's look at 10.6. Okay, we'd like to write this as a fraction times a power of 2. Well, we could write, you know, here's a fraction. We could write it as this thing times 2 to the 0, which is 1. We could write it as 101 point, this thing. Let me leave off the dot, dot, dot. We could write it as this times 2 to the 1st. Right? When you multiply by 2, you move the binary point one spot to the right. We could write it like this, times 2 to the 2nd. We could write it like this, times 2 to the 3rd. We could write it like this. And there's other ways we could do this too. All right, just like scientific notation, there's a preferred way to do this, which is to make sure there's a single digit to the left of the decimal point. This is the way we're going to want to write this number. And so we're going to store two pieces of information. We're going to store the exponent, the power of 2, and we're going to store the fraction. And we're also going to store the plus or the minus sign that's either implicit or explicit in the beginning. So we're going to code this number 10.6 by coding 3 pieces of information. Is it positive or negative? What's the fraction and what's the power of 2 we multiply that fraction by? That's the whole secret to IEEE 754.
So this wouldn't use choose complement. It would just use.
So we're not using choose complement yet. We will. It'll sneak in. But yeah, this is if we wanted negative 10.6, we would just do exactly the same thing, but we'd say, but it's negative, right? So yeah, not choose complement. Well, how do we store these three pieces of information? We just pick a certain set of bits and we say this is the sign bit, this is the fraction, this is the exponent. All right. So single precision floating point uses 32 bits. Okay. We have one bit which we use to represent the sign. That's right here. We actually allow 8 bits to represent the exponent. So if our exponent was 3, it's going to be a bunch of zeros with a 1, 1 at the end, because that's 3 in binary, right? And then we have 23 bits to represent the fraction. So we would take this number and we would extend it out until we had 23 bits. And then we just slam those things side by side to give us a 32-bit number. So 23 for the fraction, plus 8 for the exponent, plus 1 for the sign, that's 32 bits. And there's some details. We do some weird things. For example, we add what's called a bias. If the exponent is 3, we don't actually store a 3. We store a 3 plus 127. We always add 127 to the exponent. Why? Because someone decided that was a good thing to do. Some group of people decided that was a good thing to do. And so since we've got 8 bits for the exponent, and the smallest 8-bit value is negative 128, yeah. So if we store an exponent of 0, it actually means negative 127. Okay, so the exponent we store, we always add 127 to. The other peculiar thing that we do, since we're normalizing this so that there's always a single digit to the left of the decimal point, a single non-zero digit, right, to the left of the decimal point, if we know this digit is not 0, what's this digit got to be? It's got to be a 1, because every digit's either a 0 or a 1. And we're normalizing so that there's not a 0 over here, it's got to be a 1. So we don't actually store this 1 in our fraction. We just believe that it's there. So we actually store just the stuff to the right of the decimal point. So those are details, and you're not going to need to worry about those in here. You will in 250 and in 270. But for here, the takeaway is just that we're basically doing something similar to what we do in scientific notation. We're rewriting our number as some fraction times a power of 2 with a sign indicator in the front. And then those get packed into a 32 or a 64-bit number in some way. If you're using IEEE 754, it's this way. The interesting thing to look at here, though, is the difference between single precision and double precision. So single precision is a float, double precision is a double. Double is 64 bits, right? Twice as many bits. Sign bit is still just 1 bit. Okay, 0 is a plus sign, 1 is a minus sign. The exponent only gets 3 extra bits. Right, so the exponent had a max value of 256. Now it goes up to 2048. It's not a big difference in the exponent. Most of those extra bits go into the fraction. Right, from 23 bits, now we've got 52 bits of fraction. So a lot more precision, but only 2 to the 8th more exponent. I don't know if we need to go through this. Let me see where this goes. Yeah, maybe we should go through it. So if we want to store the number 2 to the 127th, right, this exponent bias, right, we add 127, we would actually store an exponent of 254. If we want to store 2 to the negative 126th, we add 127 to negative 126, we would store an exponent value of 1. There's a bunch of zeros sort of implicit to the left of any number, right? The number 5 is the same as the number 00005, right? The number 1010 is the same as 00001010, right? So we could keep shifting this over to the right, right? But the rule is we need a non-zero digit here, right? Just like when we do scientific notation, we don't put a 0 point something times, right? We shift until it's non-zero. There's one problem with this. What if we actually wanted to represent the number 0? So this is, you know, just a bunch of zeros. And if we multiply it by 2 to the 0, right? 2 to the 0 is 1 times 0 is 0. That's good. But to normalize this, we need to shift this until the thing to the left of the decimal point is not 0. That's never going to happen because all the digits in our fraction are 0. So the way this is described so far, we cannot represent the number 0. That's a problem. So there's a special way to represent a 0. There's a special combination of bits that are used to represent the number 0. And I think it's making your exponent negative 127 and then having all of your fraction bits be 0. But it's a peculiar form. And there's a few other oddities in this representation. They're not oddities, they're features, but they break the way that we've described how we code numbers. There's some exceptions to that let us do things like represent more precision for numbers that are very close to 0. There's also representations that let us represent things like positive infinity or negative infinity. There's a particular bit pattern that the CPU will understand as meaning infinity or negative infinity. And if you take 1 and divide it by 0, you'll get this special bit pattern that means infinity. And there's special bit patterns we can use to represent what's called NaN, not a number. So if you take the square root of -2 as a double number, you'll actually get this value that means not a number, because square root of -2 is not a real number, it's imaginary. So there's all these extra clever details in these representations, but you don't need to worry about those. So what's the punchline on this? For a single precision floating point number afloat, roughly 6 significant digits, and a range of roughly 10 to the 38th down to 10 to the -38th. For a double, your range goes from 10 to the 300th to 10 to the -300th. So not a big increase in range, but your precision goes up to 15 significant digits. For a double float, we have 18 significant digits, only 3 more significant figures, but a much wider range, right? So roughly 10 to the 5,000th, 10 to the -5,000th. So depending on what you're trying to do with your data, right, you might use one type or another. For us, though, stick to double. There's no reason to use a float. Again, when memory was more precious, we would use floats because it was half as many bytes if you didn't need the benefits of a double. But memory is relatively cheap, and a lot of hardware is optimized for doubles. So we usually use doubles if we're doing floating point. Long double if you really need the bigger range or more significance, but mostly we'll stick with double. And again, you know, charge an electron, mass of the sun, most of the digits that we know about are zeros because these things are approximate. So we're not really losing something by switching to scientific notation. All right, so this is some of what we already just worked through. Okay. So in C, right, we can actually use scientific notation to represent these larger or smaller numbers. So we can write something like 8e5 to mean 8 times 10 to the 5th. And if we say double x semicolon x equals 8e5 semicolon, it'll actually interpret that as 8 times 10 to the 5th. And you can use a big E, you can use a little e, you can use a plus or minus sign in front of the exponent part. We can do floats in plain old, decimal notation. 10.6 is a perfectly fine float. We can use scientific notation with something like 5 point, with an exponent specified, and so on and so forth. But you can't leave a blank before the E. So that's one place where spaces are important. Just like you can't say x equals 1 space 0 if you mean 10. Digits have to be side by side. All right, so as I said, special numbers that you can represent with these things, so plus or minus infinity or not a number. If you take 0 divided by 0, you get not a number, for example. If you do infinity times 0, it's not a number. If you divide a number by infinity, you get 0. So it kind of does reasonable things with limits, if you like calculus, as far as when you get plus or minus infinity. And we can get overflows when we work with floats or doubles, just like we can with integers. For example, if we take 2.5 times 10 to the 37th and multiply by 1,000, and we declared the result to be a float, which only goes up to around 2 point something times 10 to the 37th, that'll overflow, it'll turn the value of that into infinity. If we take 10 and divide it by 0, that'll give us infinity for big 2. If we take the difference of two infinities, that gives us what's called not a number. It's not 0 because infinities aren't all the same size. That's a topic for CSE 215. So big 3 would turn out to be not a number. So a signed character is guaranteed to be 1 byte. A short int is guaranteed to be at least 2 bytes, but it could be bigger than that. Depends on the system you're on. An integer will be at least as big as a short int, but don't know how much bigger or if it's bigger at all. A long int will be at least as big as an int. On our system we saw a long int and an int were the same size, 4 bytes. And a long is at least as big as a long int. But these are very much dependent on the compiler, which is usually dependent on the system that you're running on. And similar rules for unsigned integers. All right, so questions on that. That's like a whole bunch of wordage about representing numbers in binary or in binary coding. And I want to move away from that and start talking about operating on these things. But any questions on that? And if that's not all like crystal clear, that's okay. Okay. In other courses, we would spend a week or two going over some of these concepts. So this is just kind of high level first view, maybe.
So excuse me. The only reason we need to know that is just so you know what kind of number to. How to
Basically, yeah. If you're trying to work with something that's numbers around 10 to the 100th. And your code is blowing up and you're using floats, right? That's probably where the problem's coming from, is that floats only go up to 10 to the 37th, 10 to the 38th.
Okay.
All right, so let's do a 5-minute break. We come back, we'll start talking about arithmetic expressions.